Hey everyone, my name is Darek Kłeczek. I'm a machine learning engineer at Weights and Biases. Joining you from Warsaw in Poland. Let us know in the chat where you're joining us from. And I have the pleasure of introducing you to Jonathan Frankle. Jonathan is chief scientist at MosaicML, which recently has been acquired by Databricks. He leads the company's research team towards the goal of developing more efficient algorithms for training neural networks. You might also know him as the author of ICLR 2019 Best Paper, Lottery Ticket Hypothesis. And in addition to his technical work, he's also actively involved in policymaking around challenges related to machine learning. And today, this is the third lesson of our Training and Fine-Tuning LLMs course. And Jonathan will teach us about data and data sets for training LLMs. So this is an exciting topic. We're excited to have you, Jonathan. Thanks for being with us.
Thank you so much for having me. I'm really excited to be here and share what I know. I want to emphasize to everyone before we start, there's a lot more I don't know than I do know, and a lot more we don't know as a field than we do know. So if you came here looking for clear answers and being told exactly what to do, I'm afraid I'm going to disappoint you. But my hope is I will share with you the big questions you need to think about, the methods for trying to sort through those questions and making the right decisions in whatever context you're working in. Awesome. So let's go ahead and get started. Let me get my presentation up and then we can dig in. So I've left 3 GitHub links here and I'll keep them up. I'll bring them back in the future, but this is my frame of reference. These are the code bases I work with every day and all of us at MosaicML work with every day as we build our models. So, if you're interested in basically doing it the way that we do it, and you don't have to, there are lots of great libraries out there. This is certainly where I'd recommend starting. So to give you a brief overview of the game plan, there are really 4 things I'm going to cover. I'm going to start with a bit of friendly advice. That friendly advice is intended to kind of contextualize how we should think as scientists. And then I want to really answer 3 questions. How much data should you use? Which data should you use? And the logistics of getting the data from point A to point B. If we cover all of that today, then we've been very successful. It seems pretty straightforward and easy, if only it were so in practice. But the goal today is to at least highlight for you some of the key questions you should be asking yourself. And I am going to ask, please feel free to ask questions. I'm going to try to pause for questions after every section here, and hopefully we'll get to take a few of them. So please feel free to share your thoughts. I'd love to chat closer to the content than toward the end. So with that, I'll start with a bit of friendly advice. This is pretty generic scientific advice. It's important though. First of all, start small and work your way up. The thing that scares me most whenever a customer comes to work with us at MosaicML is when they say, hey, I'd like to come work with you and train a 70 billion parameter model. That scares me a lot because you don't just go and train a 70 billion parameter model. Even with all the great tools we have and all the great technology that we have, it's never that simple. Every problem is different. And it's very important that you start small and work your way up. I want to start with a 125 million parameter model and work my way up step by step and understand the problem better and better. Spend $1 before you spend $10, before you spend $10 million. And it's important to keep that in mind. Don't ever just shoot for the moon. Nothing that I'm going to tell you today will tell you exactly what you need to know to just shoot for the moon. It's certainly something we never do at MosaicML. Friendly advice number 2, be skeptical of what you read in the literature. And I don't say that to mean disregard what you read in the literature, but be skeptical. Think critically. The reason is that, there are really 2 reasons why I say this. Number 1 is that no paper is perfect, especially in an empirical science where knowledge is hard to come by and everything is pretty fuzzy and context dependent. It's really convenient when we try to look for simple answers, but there are no simple answers. And many papers, we're trained to present simple answers as scientists. And kind of reason 2 is that our incentives to get a paper published or get a paper to be popular and kind of advance our careers as researchers are not the same as making sure that we get useful scientific truth. They're often to hype something up. They're often to get an idea widely circulated. They're often to get through the review process, and that means making things simple and clear and making it look like you have a very obvious win when sometimes you don't. And so this isn't out of malice on anyone's part, but it is important to be skeptical of what you read in the literature. That it's true in the way that it's stated, and that it's true in the context of your problem. And so the important thing I tell everyone on my team at Mosaic, and we practice here, test everything for yourself. Don't believe it just because someone else said it, and don't believe anything I say today just because I said it. Test it for yourself. Point number 3, and this is going to sound very repetitive, don't trust your intuition. Test. Intuition is great for posing hypotheses and coming up with ideas. Do not try to intuit your way through it and then make decisions about what to actually do. Test and measure. Compare to strong baselines. Compare to simple ideas. Compare to things that would be true if your intuition were completely wrong, and find out what the data says. You may have excellent intuition, but if you do, you're a far better person than me. I have terrible intuition. I tend to be wrong a lot more than I'm right, and that's fine because I pose hypotheses, test them, realize I'm wrong, and improve. The last piece here, and I think this is kind of, a little bit even higher level than the other points. When people said data science in, yesteryear, 5 years ago, 10 years ago, I kind of thought it was a bit of a buzzword. The things we're going to discuss today are really literally data science. You are working with data and you need to be a scientist. You need to pose hypotheses, test them using experiments, run control experiments to make sure that your results are actually meaningful and significant, all of that good stuff. There are no answers here. You have to be a scientist and let the data speak for itself. I hope this is helpful framing. This is how I think about the world. This is how we operate at MosaicML. These are key principles for us, and especially in the data realm where we know far less than we wish we knew, and we don't know much more than we do know. This is the only way that you can operate and make good decisions. What I like to say about deep learning is that the path to enlightenment is starting by accepting you know nothing. I think the biggest mistake we make as a field is that sometimes we assume we actually know things. We don't. And much of what we think we know is completely wrong. So start from that Zen place of lack of knowledge and build knowledge using science and using data. Okay, that concludes my friendly advice, and now it's time to actually talk about the other part of point 0, the surprise that isn't actually in the lecture, but wasn't in the agenda, but I do want to cover it, evaluation. You can't make any decisions until you know what success looks like. When someone comes to me and says, I want to build a language model, what data should I? My answer is, I have no idea because I don't even know what you're trying to accomplish. And even if you wanted to make progress in this problem, you would have no idea if you were successful. The scariest thing in the world for me is when a customer comes to me, pays a lot of money, trains a big model, and then turns to me and goes, so is it good? If that question is getting asked, then something went horribly wrong in the process because we didn't set up good evaluation frameworks for measuring whether our model was good. I wish I could tell you which benchmarks to use, and I have given you a link here to our MosaicML LLM evaluation page where we're trying to put together, where we've shared the evaluation harness and the evaluation benchmarks we currently use so that you know exactly how we're measuring our models internally and making decisions. But evaluation is not a one-size-fits-all process. We're evaluating among a bunch of different axes. I can actually show you. We're looking at a lot of different kinds of models. These radar plots have gotten very popular lately, but we're looking at everything from programming ability to common sense reasoning to reading comprehension. We've taken as many benchmarks as we can find out there that we think are good, kind of taken them apart and put them back together into these categories and then looked at our model on these axes. This is not the right way to do it, but it's a useful way for us and we found it to be productive. This will not be the right way for you to build your model because chances are you're building your model with a specific purpose in mind. So are we, but our purposes are probably different. And that means you need to evaluate differently. Until you have a way to measure whether your model is getting better at the things you care about, you shouldn't even begin to try to train a model. Evaluation is the most important and the hardest part. So just as a reminder, please, think about this. And I will say, you can access this whole evaluation harness on GitHub. This is not meant to be marketing, but I do want to put good tools in people's hands. There are a lot of other great evaluation harnesses out there. Luther AI has one that's very useful as well. This is the one we use at Mosaic. You can go to this URL, you can go to our LLM Foundry repo and go to the evaluation area, and you can go and run on any Hugging Face compatible model. You can run this evaluation harness and see for yourself. So I think it's a great set of tools. I hope it's useful to you. It's what we use internally and we wanted to share it with everyone. But the most important lesson here, before you even touch data, before you even begin to think about how you actually build your model, you need to know what success looks like. And I don't like to work with any customers until they have a way of measuring what success looks like. Okay, that's all for the friendly advice. Let's talk about data. So I'd promised you 3 questions. Question number 1 is how much data? How much should you use? And there are 2 steps to any model training process. There's the pre-training process and there's the fine-tuning process. Personally, I will say I hate the phrase fine-tuning because often fine-tuning is not very fine. It tends to actually be as intensive or more intensive than pre-training. But pre-training tends to be generic and self-supervised. We're just training on next token prediction. Fine-tuning tends to be much more with a purpose to improve the model on a specific task, on a specific domain, on something like a chat or instruction following, or on a particular language like Python, or a specific, an actual human language as well. Whatever it may be, you want your model to learn about a domain, learn about a task, or both. So I'm going to divide how we talk about data into both of these components because they're both very important. And I'm going to talk about this in the context of building a model from scratch because honestly, I think that's the most fun part of this. But even if you're just fine-tuning a model, and I say just fine-tuning a model, there's no such thing as just fine-tuning a model. You're going to still need to use a lot of these lessons and think about how much data and what it will cost you as well. I'm really big on trying to measure things in dollars and cents in addition to just pure volume. So actually, before I show you some chinchilla plots, there are 2 papers that I've highlighted here because I think they tell 2 different aspects of a very important story. So imagine I said to you, I'm giving you $1,000 in MosaicML A100 credits. Go train the best model you possibly can. How are you going to spend that budget? And suppose I give you a fixed data set. I'm just going to tell you, here's the data set you have to use. Here's the model architecture you have to use. But I'm not going to tell you how big of a model to use. You could use a very small model or a very big one. You could use 1 billion parameters or 100 billion parameters. And I'm not going to tell you how much data to use. But I will say I've given you a fixed budget. So if you train a bigger model, that means it's going to be more expensive for every piece of data you look at. So you're going to get through less data. If you train a smaller model, it's going to be cheaper per piece of data you go through. And so you can get through more data. So the size of the model you choose determines the amount of data you get to see. What is the best trade-off? Clearly, if you have a model with 1 parameter, you can look at huge numbers of tokens, but it's going to be pretty bad. If you have a model with 10 trillion parameters, you might get to look at 1 token, and that's also going to be pretty bad. So there's a sweet spot somewhere in between here. There's a right model size and a right amount of data that will get you the best results. That's what that first paper, Training Compute Optimal Large Language Models, also known as the chinchilla paper, that's where kind of the chinchilla scaling laws come from. That's the question that paper was trying to answer, and what previous work from OpenAI was also trying to answer. If I give you a fixed budget, what is the best way to spend it on model size versus amount of data? And this will tell you for any particular budget, here's approximately the right size to go with, and I'll show you that in a moment. Now, the Llama paper that came out this spring, in some sense, violated convention because they purposefully chose things that were not optimal. They purposefully chose smaller models on more data, which meant that for the amount of money they were spending, they could have gotten a better model. Why did they do that? Like, why did they spend their budget less efficiently than they could have? Because spending your training budget efficiently is not the only constraint. Smaller models are easier to fine-tune, they're easier to do inference on. In fact, they're even easier to train for a lot of systems-related reasons. And the Llama authors make the point in the paper that they purposefully chose to train smaller models on more data to do something highly suboptimal, according to that first paper, to make it easier to train and easier to work with and easier to do inference on. That's a totally reasonable choice. And the question just becomes kind of, what is the trade-off you're willing to make? What is the penalty you're willing to pay from that chinchilla optimal model in order to make sure that other things are easier? And I think that's a key question that comes down to choosing the right amount of data. So I'm going to show you, I believe, 1 and only 1 graph during today's presentation. This is a graph from the chinchilla paper. And this is kind of the whole paper in 1 graph in some sense. So let me walk you through this a little bit. On the x-axis is the number of parameters in a model. So as you get further to the right, the models get bigger. And each of these points is some model that was trained. On the y-axis is the training loss. So, how well did the model do? Lower is better. Lower loss means you got a better model. So what I want you to do is take a look, for example, look at that point that says 3B or 3 billion parameters on the x-axis and kind of trace your way upwards. Look vertically upwards. you'll see how for that same model size, you can get a lot of different losses, anywhere from a very high loss to a very low loss. The difference here is how much budget you spent. So each of these different colors, each of these different curves is a different budget. Those numbers in that legend of the plot are different budgets in terms of flops, anywhere from 6E18, that's the uppermost curve, to 3E21, which is almost 3 orders of magnitude more compute. And you can see, for example, again, tracing that 3 billion parameter model, looking at that vertical line up and down, you can see that as you increase the budget from, the top curve where it overlaps, which is 6E19, I believe, or yeah, 6E19, all the way down to that bottom curve, you're getting better and better loss as you increase your budget. That makes sense, right? You spend more. And when I say increase your budget, what's happening? You've got a fixed sized model. So when you increase the budget, you're training on more data. So one way to think about this is if you look up and down any one of those vertical lines, you're looking at that 3 billion parameter model trained on more and more and more data. Okay, so let's look at any one of these curves and pick a curve you want to look at. Notice that the curve kind of goes up on the left, up on the right, and down in the middle. What this means is for any given budget, for any given amount of money that you have to spend, there's an optimal number of parameters that will get you the best loss. For example, if you look at that second curve from the bottom, the 3 billion parameter model is kind of right around the bottom of that curve. That means that if your budget is 1E21 in terms of flops, a 3 billion parameter model is the optimal model size. If you have a bigger model, you're not going to do as well for that same budget. If you have a smaller model, you're also not going to do as well for that same budget. And so for the amount of data, then you can determine the amount of data by looking at, I've got a 3 billion parameter model, this much budget, and then you can go back and back calculate the amount of data that you need. So this is a really important observation. For a given budget, there is a right model size and a right amount of data that will get you the best possible results. And there's kind of a nice thing that follows onto this, and I'm not going to highlight here, which is actually, there's kind of a fixed relationship between budget and model size. Approximately speaking, what the chinchilla paper tells us is that the right amount of data is about, for a particular model size, is a number of tokens equal to 20 times the model size. For a 3 billion parameter model, that means 60 billion tokens is kind of the optimal way to train that model. Now, the other important part that you can take away from this plot, which I think is really interesting, and that's why I've chosen this particular plot from that paper, is, again, let's look at that second line from the bottom where the 3 billion parameter model is optimal. You can also ask yourself, how suboptimal would I be if I were to choose that same budget but have a smaller model? Let's look at where the 1 billion parameter line comes in. You can kind of see that you're going to give up, about 0.05 in loss, which may or may not be significant to you. But that's the trade-off the llama authors were making in some sense. They're going to spend their budget suboptimally, which means the models are going to be worse than they could be for that same budget. But that's a worthwhile trade-off for them because they were able to get models that were easier to serve. So the llama authors, in many cases, were picking a point for any one of these curves that was off to the left. It was not the very bottom point, it was somewhere off to the left. But to them, that made sense, and that was a reasonable trade-off. And given the popularity of the llama models, that tells me it was also a very popular trade-off that people were happier with. If they had done chinchilla optimal models, and by chinchilla optimal, I mean picking kind of that bottom point, picking data equal to 20x parameter size, those models might not have been as popular because they would have been much harder to deploy. So this is a really important graph. I think in some sense, this is the most important graph if you're looking at the question of how much data should you use and how should you choose your data. So I want to keep moving a little bit and ask, okay, so where do you get your data and how much does it cost? And the nice thing is for pre-training data, there are a bunch of amazing data sets that are out there. Everything from the pile, which was a visionary data set by the people at Eleuther AI. And I say visionary because they made an open source large scale data set in like 2020 and 2021, back before anybody else was really thinking about this. Everything up to much more recent data sets, like the Red Pajama data set from Together AI, or the Falcon Refined Web data set from the folks who made the Falcon models, the StarCoder data set, which is a data set of permissively licensed code, which we found really useful at Mosaic, and the Dolma data set that just came out from our friends at the Allen Institute for AI, which looks really promising. These data sets are big, they're free, you can download them, and you can use them to build models. These data sets mostly contain web scrapes. And web scrapes tend to be useful. There are a lot of tokens. And I just mentioned to you, we talked about, if we go back to that previous slide, 3 billion parameter model, we said 20x. So let's take the 70 billion parameter Llama 2 model, for example. The optimal amount of data there is a 1.4 trillion tokens. That is a huge amount of data. I'll go through in a moment how big some of these data sets are so you can get a sense for kind of what the trade-off is, but that is a massive amount of data. You need probably a solid 1 trillion to 3 trillion tokens to train a modern large language model. And the only place you're going to find that as of right now is scraping the web. That's why we rely so heavily on web scrapes right now. We supplement with all sorts of other great data sets out there, Wikipedia, GitHub, what have you. But at the end of the day, you kind of need the whole web. And the web is massive compared to some of these other data sets. I'll show you that in a moment. Now, I also want to talk briefly about after training data. And I'm going to highlight a few things here. First of all, I'm going to highlight how much it costs. Now, after training data, I'll give you, just some examples so you kind of know what I'm talking about here. Once you've trained a model, that's not enough. You can think of like the original GPT-3 where you had to really prompt it carefully versus, say, ChatGPT these days, where it just follows instructions. And the way that you get there is by fine-tuning the model afterward on instruction following tasks. You literally give it instructions and responses. Write me a poem about deep learning in the style of Shakespeare, and then an example of a poem, or write me a program that sorts a list, and then a Python program that sorts a list. You give it a lot of examples of that sort of stuff. And I'm highlighting a few things from the Llama 2 paper because they did a fabulous job, the authors of that paper, in terms of highlighting what you actually need to do. They said that we found that SFT, which is supervised fine-tuning, and in this case, instructions and responses, annotations in the order of tens of thousands was enough to achieve a high-quality result. We stopped annotating SFT after collecting a total of 27,540 annotations. So those are, I've kind of put some rough costs here. These are costs I've gotten from, I've heard from friends who are in the field who are collecting this data. This is if you work with data labeling firms that do a very professional, excellent job on this. It's about $30 to $50 per example. There are some open source data sets, but they're a little bit spottier. And the licensing on those data sets is a little bit more questionable because a lot of them were created by scraping from GPT-4. And there are terms of service that may or may not allow that for GPT-4. So the first part here is that you generally do kind of this supervised fine-tuning or instruction following. And I also mentioned at the bottom a multi-turn chat conversation. You can imagine instead of one back and forth, you have, let's say, 7 total, one person says something, you and the model going back and forth. That tends to cost on the order of, from what I've heard from friends, about $100 to $200 per conversation. So again, this is quite expensive. About 30,000 annotations times about, let's call it $50. And, you can do the math. That's $1.5 million right there that Meta might have spent here. Now, there's something interesting that Meta also said in this paper that I think is worth highlighting. Surprisingly, we found that output sampled from the resulting SFT model, the model that was fine-tuned on this 27,000 example data set, were often competitive with SFT data handwritten by human annotators, suggesting that we could reprioritize and devote more annotation effort to preference-based annotation for RLHF. So I did not work on this paper. I have no inside information. But what this indicates to me is probably they used a lot more than 27,000 examples, but they had Llama 7db generate more examples because they found that that worked pretty well. And they could kind of have humans curate those examples, get a little human input, and it was much more cost effective from there. So it's something to think about. And a lot of these models like Llama 2 have licenses that restrict you from using the model to generate data to train other models. And I think it's specifically because you can now do this kind of thing. Now, there's one other piece to doing after training data, and that's RLHF, or reinforcement learning with human feedback. The idea here is that, there's having instruction following, but there's also just trying to make sure that the model produces outputs that humans find helpful, find safe, that humans prefer. And the way that you typically do this is you provide 2 different outputs of the model, and you have a human say, I like this one better than that one, or I like that one better than this one. There are much fancier ways of doing it, but that's kind of the high-level idea. And Meta did this iteratively. They took their model, they fine-tuned it, then they did some RLHF, they did this pairwise comparison, updated the model based on that, took that updated model, did another set of human feedback, did another round of this, and did this a bunch of times. And in total, they collected 14 batches of human preference data on a weekly basis, consisting of over 1 million binary model generation comparisons. At $5 to $10 per comparison, you can do the math. That's pretty expensive. And so when I think about cost of data, not just kind of right amounts, but cost, this is kind of what it takes to build a large-scale general purpose model. Now, it's important to note not everyone, and hopefully, almost nobody who's listening to me talk right now, needs to build a general purpose model. So, a lot of people are trying to build very specific special purpose models. And with that in mind, you need a lot less data on both fronts. If you're fine-tuning an existing model, you need a lot less data than this, but it is worth making sure you keep in mind your data budget or where you can get data that looks like the actual interactions that people are going to have with the model. That could be existing data that you have from a previous model or a previous setup that you have. It could be that you go and actually procure that data, that you have some other data that can kind of fill that need, but it can get very expensive. We have a question from YouTube. How useful can data augmentation be in expanding out these data sets? Can you make a 1 billion token data set reliably into a 3 billion token data set with augmenting, or not that much? So data augmentation is a tricky topic because what I just discussed in some sense was using a model to generate more data for kind of instruction fine-tuning or SFT supervised fine-tuning. Now, data augmentation for pre-training data is something that hasn't worked very well as far as I've seen. I've seen some papers that discuss it and propose ideas, but I don't know of anyone who's using it in practice right now. So no, I wouldn't rely on data augmentation at the moment. In computer vision, and I come from the computer vision world originally, data augmentation is very, very useful. But I think the answer in computer vision is that when we have an image, we have a lot more information intrinsically about that image. In most contexts in the real world, we can left, right, flip things and it doesn't matter. We can crop things differently and it doesn't matter. It's much trickier to think of something equivalent to that for text. You can't kind of left, right, crop a sentence, or left, right, flip a sentence, or crop a sentence, or change the aspect ratio of a sentence. So text is just much harder to work with in that respect than images. Images, we just kind of know a lot more about as humans and have a lot more priors we can impose to kind of take a small amount of data and turn it into more data. It's a great question, but as of right now, we don't have a good way to do that. So I want to pause here for any other questions on this first section before we move on to the second section of which data you should use. So, Dark or Taylor, if there are any other questions that folks want to ask, now's the time to get them in.
We have a couple of questions also from Visible. So the first question is on chinchilla scaling clause. And it is the question is it for a fixed architecture? What about same number of parameters but different model types?
So it is mostly for a fixed architecture. They're kind of scaling rules that we generally use to create standard style 1 billion or 3 billion or 7 billion or what have you parameter models. As you play with the architecture, though, those scaling laws probably change. Chinchilla is still a good rule of thumb as a starting point, and it's very expensive to go and compute your own scaling law. If we kind of go back to that graph, look at the number of points that they have and imagine going and doing that before you train a model. You'll spend orders of magnitude more compute creating these scaling laws than you will actually training the final model. So it's not affordable for all of us, even at Mosaic, certainly not, and we have a lot of compute available. The DeepMind folks put in a lot of time and money into this. So the answer is, as you change the architecture, these scaling laws almost certainly change a little bit, at least. But Chinchilla is still a really good rule of thumb as a starting point. And finding a good starting point is the whole name of the game here. Beyond that, you do have to do the science to figure out what makes sense for you. A great question.
Thank you. There is also a question about synthetic data. Do you see that useful for pre-training at all?
It's a tricky topic. It's not something that I've used personally, but I do see a lot of people talking about it more and more. But I'm still pretty skeptical because at the end of the day, where does the synthetic data come from? It probably comes from a model. And this isn't scientifically backed, this is intuition, so take it with a complete grain of salt and disagree with it. But I'm not a big believer that you can just create something from nothing. That many of the strategies that seem to work best for using a model to create more data involve some human curation or human involved. Everything from having the model generate a couple of candidate examples and then having a human choose the best one or edit, one example that they prefer, to even things like constitutional AI, which Anthropic advocates for, where you have the model produce an example, then you give it a principle from a constitution that a human has written and ask the model kind of update this output to make sure it's in line with this principle. That's still kind of using human input. And so I think the art is in reducing the amount of work or kind of using each human hour as effectively as possible. But I'm kind of skeptical of the idea that we can simply create something from nothing. And synthetic data is more along those lines without some kind of human input or human curation. But again, that is just intuition. So take that with a huge grain of salt.
Thank you. I wanted to go back to your comment about evaluation and the fact like you should start with figuring out like what do you expect this model to do, and you mentioned some of the benchmarks. that are typically used to evaluate LLMs. But I wonder for companies that want to train their own LLM, and by the way, there is a question like when you should think about training your own LLM versus just using one that is already available. But if you want to train one for your use case, like do you have any advice how to think about evaluation?
Yeah, so evaluation is the hardest part of the whole thing. The gold standard of evaluation is using humans or putting it in a real world setting and seeing how people interact with it. I think code completion, things like GitHub Copilot are a great example of this. You can put out a model into a real world setting and see how many people press tab and actually accept the result of that. That tells you a lot about how well your model is doing and whether you need to do better. So the nice thing for a lot of companies especially is you're typically not putting this model in a brand new use case. You're typically integrating this model into a flow that already exists. And this is augmenting humans or this is automating something. And I hope you already have a way to measure success of that use case in general, in which case you can look at how the model impacts that result, or how you're measuring humans today, or how you're measuring the existing process or the existing model. But when it comes to evaluation, it is incredibly bespoke and incredibly tricky, and it is much more art than science right now. I would say there's almost no science. I will also caution people, there are a lot of publicly available benchmarks. There are things like Helm and MMLU. I think they're all terrible. I think every single public evaluation that we have right now is terrible. I don't trust them as individuals. I don't trust them as composites. I don't even trust our own Mosaic evaluations to a certain extent. I think we're doing the best we can, and it's okay to do the best you can, but that doesn't mean you should take any of this as the gold standard, or you should look at a leaderboard and say, this model was better at Helm than that model, therefore it's a better model. That's just not true. These are pretty bad benchmarks. You should go, before you ever rely on one of these benchmarks, go actually read the benchmark. They're generally not very long. You can look at a few questions and ask yourself, is this a good test of what I want the model to do? The answer is almost certainly going to be no, unless your model is answering multiple choice questions or answering like questions about physics or what have you. It's almost certainly a pretty bad test of what your model can do relative to what you want it to do. It's the best we can do, but it's the reason why you should be building domain-specific evaluation. And you had mentioned, that one other question of when should you build your own model? And the answer is really that first principle I gave you all the way back at the beginning. I'm even going to scroll back to it just, to put it out there. Start small and work your way up. By which I mean, if an existing open source model solves your problem effectively, you're done. Go home. Take the win, be happy. If GPT-4 solves your problem and you can use GPT-4 and the cost is okay, take the win, go home. Worry about other things, work on harder use cases. The folks who come to me either can't use GPT-4 or GPT-4 doesn't address their problem or an open source model doesn't address their problem. And when they come to me, the first thing I tell them is go fine-tune an open source model and see if that works. Fine-tune one of ours, fine-tune Llama, fine-tune Falcon, what have you. And if that solves your problem, good. Take the win, go home, you're done. We get to pre-training when none of those things work. And there are a lot of cases where none of that stuff works, either because you've got a very specific domain, you've got a lot of data, what have you, but work your way up, climb the ladder, start small. Don't go straight for the big stuff right away. You'll know if you need this. Any other questions at this stage, or should we move on to the next section?
I think let's move on, and we'll still have some questions. We can keep them to the end if we still have time.
Okay, so the next question is which data? And I wish I had a good answer for you on which data. There are more questions than answers here. But I am going to tell you kind of what exists and how we think about it. And I'm going to start by giving you a bit of an exercise. I'm actually going to be quiet for 1 minute. And for those who are watching, get out a sheet of paper or think to yourself. What I've done here is I've taken a table that we put in the MPT blog post. Here are all the data sources that we had. And I'm going to go through them with you one by one just so you become familiar with them. What I've hidden here with these question marks is what proportion of the data set to you, or what proportion of our overall data mix should come from each of these data sets. There's no right answer here, but I think it's a fun exercise to have to think this through. On the left, you'll see that it starts with 3 different common crawl data sets, 3 different web scrapes. MC4, which is a big multilingual, although we've just picked out the English portion here, but it's a web scrape, and it's actually web scrapes going back over several years. And it's 2.4 trillion tokens. That's a lot of tokens. We have C4, which is one web scrape from 2019, about 100 billion. Red Pajama Common Crawl, a more recent one, about 900 billion tokens. Then we have a few other things. We have the stack selected languages. This is from the stack dataset from StarCoder. It's a bunch of languages from GitHub. We focused on the common ones like Python and Java and C++. Wikipedia from the Red Pajama dataset. This is just a scrape of Wikipedia, about 5 billion tokens. The markdown component of the stack, this is like readmes and things like that, so it's more text than code, about 100 billion tokens. Semantic Scholar is now a dataset known as Pesto. It's about 50 billion tokens of open access scientific papers. The books dataset, as Red Pajama prepared it, a scrape of the LaTeX from Archive as Red Pajama prepared it, and Stack Exchange as Red Pajama prepared it. These are all the inputs for MPT models, and you have some tough choices to make here. I want you to go and figure out how would you get to 1 trillion tokens? You could get there really easily by just using MC4 and using a web scrape, but that's, the web scrape is okay. It probably has a bunch of HTML that hasn't been stripped out of it. It probably has a lot of advertisements and low quality pages. You could also get there by going through Wikipedia 200 times. That's a lot of repetition, but Wikipedia is a pretty high quality data set. You could go through the stack selected languages, twice. That's a lot of code though. Do you really want a model that just does code? So I'm gonna actually pause for 30 seconds. I want you to think about this. This is an exercise where if we were sitting together in a room, I would ask you to write it down and share with me. But I'm curious for you to do this, and I'm not sure how interactive we can be here, Dark, but I'm kind of curious if anybody wants to, share what they thought. I'd be really curious to hear responses if anyone wants to post it. So take 30 seconds and kind of think about it for a minute. I love this exercise.
Let's see if there's any response on our stream chat.
Yeah, no pressure, but I'm always curious. If we were in a room together, I would definitely be calling on people and asking them, what do you think?
Maybe I can try myself.
Yeah, I'm curious. What would you do here?
I feel like a lot of deep learning is being like a little bit of a magician and just ingredients and trying to see like what comes out. I think the challenge with like these LLMs is like it's very hard to do a lot of experiments because they are super expensive. So I would say I would probably like do more of the high quality data sets. I heard a lot about code being important, so I'd probably like use a lot of GitHub or the Stack.
I don't. You're not being specific enough. I want percentages here. Give me some percentages in some of these data sets. Talk to me.
Okay. Yeah, I don't have the numbers worked out, but I would probably use like 60% of like the different web data. And I don't know how to divide between them. I need to learn a bit more. Maybe 20% code and 10% Wikipedia, Semantic Scholar, books, and or like 15 and 15, like 15%, like all of the, let's call it like the high quality data sources. Okay, so I made up my mind. So 70% would go for web in general, like a mix of what's there. 15% would go into like the different code data sets, and 15% would go into like books, Wikipedia, archive, like all of these higher quality sources.
Why that balance? Like, why only 15% code and not 50% code? Why only 15% high quality and not more? Like, talk to me a little bit. Walk me through your decision here.
It's very much intuition. Now that you're asking, like, I think like there isn't maybe that much code. Like it would like there would be a lot of repetitions. Like I need to look in detail at the numbers, but I assume like if we do more percentage of code, like we would need to do like many epochs over the same code.
You actually have plenty of code here. So you've got, if I want you to come up with 1 trillion tokens, and you've got 463 billion tokens of code. So you could just go through all the code twice and be fine. It turns out there's a lot of code. So this is, I'm being unfair to you right now. I'm being unfair for a specific reason. I didn't even tell you what kind of model we were building or why. If I told you we were building a code model, you'd probably answer very differently than if I told you I was building a model to be good at trivia. So, again, this is a great moment for me to repeat to everyone and kind of, make fun of Dark a little bit on this. Evaluation, evaluation, evaluation. You need to know what you're doing before you can even start to ask this question. But with that said, I'll show you what I came up with. These are the proportions that I chose. So I went with about, honestly pretty similar to what you chose. I went with about 70% of the web crawls, went with about 10% code, and then the remaining 20% or so was spread over these kind of higher quality data sets. If you look in that rightmost column in the table, this is kind of a cool part. You can look at the epoch. So how many times would you go through each of these data sets? You can see I only went through 15% of MC4, but I went through Wikipedia 8 times. And we do tend to see that going through data sets too many times, you do start to, you get diminishing returns. We saw beyond 4 to 8 times of going through the same data set, you see some diminishing returns here. This is not to say, what I want to emphasize to you, do not look at this and say, Jonathan knows the answer. I chose this late at night after trying a bunch of different things and kind of giving up and saying, I don't have the quality of evaluation to tell the difference. We've gotten a lot more sophisticated since then at Mosaic, and I would do things very differently going forward. We're trying to make some choices for some new models that we've been cooking up lately, and the same applies. Like it's a tricky thing, and the real answer is know what you're evaluating on, and then try to explore which data sources seem to work best for what you're evaluating on. I wish I had a great answer, and I could tell you what to do. This is what the Llama folks did in the Llama 1 paper. And I assume they didn't do anything too differently in the Llama 2 paper. You can see kind of similar, about 82% common crawl in C4, that's web scrapes, only 4.5% GitHub. And we did find anecdotally that our MPT models were better at coding than the original Llama models. And, so this does matter a little bit. And then, about the remaining, 15% or so from these other higher quality sources like Wikipedia, books, Stack Exchange. So notice that I've used intuition a lot here. There are a lot of key questions here that really matter. First of all, should you even mix data at all, or should you just say fresh tokens are better? Just if you have a new token, use it, and whatever the proportions are, they are. If Wikipedia is only, 0.5% of your data set because it's only 5 billion tokens, that's fine. You only see Wikipedia once. Maybe that's the right answer. Now, obviously, this doesn't make sense in the limit. If you have a lot of very low quality tokens, that probably seems bad. But again, don't trust your intuition, trust the data. And so kind of this next question, quantity or quality? I think, Dark, you and I both erred on the side of quality. We wanted to make sure there was some quantity, but we did way overemphasize some high quality data sets, because intuitively we must think high quality data like Wikipedia that's more important. Maybe, or maybe not. Test it, find out. Find out what matters in your application. There's no reason to trust our intuition here. So test it, and test it on a small model. You don't have to test it on the full thing and train 10 models. Try it small. The beautiful thing about Chinchilla is that as you increase the size of your model, you should also increase the amount of data. So the cost of training a bigger model basically increases quadratically, which means it doesn't cost you that much to train a lot of small models before you train one big one. And so you can actually do a decent amount of experimentation and not blow your budget. There are questions about whether you should deduplicate. So I'm going to dwell on deduplication for a moment. I'm not going to tell you what to do, but I do want to highlight the questions that are out there. And the answer is, again, try it for yourself. There's this really seminal paper by Catherine Lee and colleagues at Google Brain at the time on deduplication. And I'm actually going to pull some lines directly from the abstract here because I think it's so well written and it says everything I wanted to say, but better. We find that existing language modeling datasets contain many near duplicate examples and long repetitive substrings. And this actually has an effect. As a result, over 1% of the unprompted output of language models trained on these datasets is copied verbatim from the training data. So the duplication of these sequences leads to memorization. Now, I think it's important to say, specifically what they were looking for. We developed 2 tools that allow us to deduplicate training datasets. A lot of these tools there are many versions publicly available to do this. For example, removing from C4 a single 61-word English sentence that is repeated over 60,000 times. So I think the key takeaway from this paper, I think a lot of people read this and say, we need to deduplicate everything. We can't have any duplicates. That's not what this paper is saying. This paper was finding things like marketing copy, and you can look at some of the examples here, or other kind of form text that was repeated tens of thousands of times in the data set. And removing those tended to lead to better results for the model and less memorization, and also saved you some time, because why should you see that example 60,000 times? But it's important, don't overread into this. This was about highly repeated examples. This is not about something that's repeated twice. And it's an important distinction there. Now, there are much fancier data deduplication techniques that have come along in the time since. These include looking at semantically related text, not just identically or near identical text. So things that where you embed your data and then you look for embedding similarity and remove things that are too similar because they're probably near duplicates. This is, this is another fancier method that can push it even further. Now, what I will say is that for all this deduplication, I would say the jury's still out and there's a lot of debate over whether this is good or bad for your models. And so the answer, you can probably say this answer directly to me without me having to say it to you. Do the science, test it, and find out in your application. There's no right answer here. These are tools, but you need to figure out whether these tools make sense for you. So that is the conclusion of the second section of kind of what data should you use, how you should choose it, how you should mix it, what's available to you, any kind of cleaning you should do. I want to pause here again to see if there are any questions before we move on to the last section here, and then we can wrap up.
There is a question about the mixing of tokens during the training, like the various. So do you just randomly mix everything, or is there some sequencing in how you feed data into training the model?
This is a tricky one. So this is another intuition that doesn't work in practice. We have this idea in our head that we as humans, we learn in curricula. You don't go and like randomly learn calculus mixed in with learning fractions as you grow up. You learn, you learn basic arithmetic first and work your way up to algebra and then calculus. And we all have this intuition, me included, that there should be a right order to present the data to the model that will allow it to learn better and more effectively. Maybe easy examples first and hardest later, or what have you. I have seen little to no evidence in the literature that there are any methods that generally work for developing curricula. There are papers coming out every year. I've never seen anything that generally works beyond, say, CFAR10, a small image data set. So when it comes to curricula, if there's no right answer, the answer is randomly sample. Now, there are questions about there's a lot about how you randomly sample. In the llama papers, when they do data mixing, they actually mention that they make sure each batch has the same proportions as the overall data set. They'll sample, 3 examples from the web scrape and 1 example from code or what have you. At Mosaic, we haven't done that. We found that in vision models, this did not help. And I don't know if we've even tested it in text models, but you can look to the llama authors for a strategy there. Whether this matters, test, and find out. Be a scientist. That does definitely seem like a lower order concern than, for example, making sure you have the right data sources or making sure that you've got the right data mix. But it is a question. So kind of curricula, I wouldn't think about that too much in terms of how you compose your batches. A little bit trickier and, open to debate right now. I don't think there's a lot of evidence one way or the other in the literature beyond that some people have chosen one thing and some people have chosen another. But often people choose things for reasons that may not have anything to do with that they're a good idea. It may have been arbitrary or it may have been just a technical reason based on how they built their code base that one made more sense than the other. Any other questions that we should chat about?
Maybe one more question, which actually asks about fine-tuning, but I want to maybe open this up to a broader answer. And this is about non-English data. And the question is whether, like, if you have a model that is trained on English, can you fine-tune it on other languages like Spanish or German? But I guess maybe if I can open this up to like more broadly, like how to go beyond English.
Yeah, going beyond English is tricky because the world is mostly in English as you start looking at text. Wikipedia in English is much bigger than any other Wikipedia. And if you look at MC4, I'll go back a little bit to this page. MC4 the M stands for multilingual. This is a wonderful data set that's publicly available that has tons of data in lots of languages. It's about 12 trillion tokens, of which 2.4 trillion tokens are English. So it is still majority English, but there are lots of other languages in there. And for people I've worked with who did have a specific need to train on a particular language, they have used the subsets of MC4 for that language. So there are multilingual data sets out there. In terms of fine-tuning on another language, once you've got an English language model, the honest answer is I'm not entirely sure. There's trickiness in the tokenizer there. That your tokenizer, and I think we're going to talk about tokenizers in a couple of weeks, but your tokenizer may have been built with English in mind, and so may not respond as well to other languages. And if you need to change your tokenizer, you probably need to pre-train from scratch. But by and large, any model that's seen a lot of English has also seen a lot of other languages. We trained MPT exclusively to be an English language model. It does actually really well in other languages. We have lots of hypotheses for why. We actually point to the markdown subset of the stack, which was not filtered for any particular language and probably has a lot of really great, rich multilingual content for people who are writing markdown files in lots of different languages. So it's hard to say for sure, but your best bet is probably to pre-train a model in that language. But I'm guessing that you could do pretty well fine-tuning a model because even when you attempt to build an English language model, it's going to see a lot of multilingual data regardless.
Thank you. I think we can move on to the next topic.
Awesome. So let's move on and wrap up. This is going to be pretty quick, and then I'm ready to wrap up. So I want to talk about logistics here. This is really hard. You have terabytes or petabytes of data. Where in the world do you put it? How do you get it to your actual training cluster? Because the data may be in a completely different place. How do you shuffle it? How do you ensure determinism? There are just a lot of logistical challenges here that will cause you a really hard time. Even things like, suppose you're training your model, and midway through, one of your GPUs dies and your model crashes, and then you have to pick up again in the middle. How do you make sure you actually pick up where you left off? And how do you make sure you don't have to spin through the whole data set to get back to that place where you left off? That would take a very long time for one of these big data sets. There are lots of solutions out there to these problems. There are lots of strategies here. I'm just going to highlight one, which is at MosaicML, we have our own data loader. It's freely open source. You can go to github.com/mosaicml/streaming. And the goal here was to address basically all of these concerns. So what we do is we have kind of our own proprietary format. It's proprietary as in it's specific to this data loader, but there's nothing fancy about it. It's just a row-based format. We break the data set into very big shards. And you can actually keep those shards in just an S3 bucket. You don't have to put them in like fast storage. You don't have to put them in solid state storage or anything like that. And a streaming data loader basically handles the rest. It will load those shards to wherever is happening, wherever the training is happening. It'll cache them to disk. It'll keep them in memory. It'll shuffle for you. It'll even ensure determinism, so you can pick up where you left off even after a crash. Even after you change the number of GPUs, it can guarantee determinism, which is really cool. It's been very valuable for me because I'm a manager. I typically don't train models myself that often, but when I do, I'm kind of squeezing them in wherever things are available, and sometimes I have to, move them up or move them down. So I found our streaming data loader to be really valuable. There's a really nice GIF that our team put together kind of showing what happens. You've got all these shards, it loads them onto the nodes, and then it shuffles and divides the individual samples up onto GPU workers. I just find this mesmerizing to watch. But personally, I found this to be really valuable. The nice thing about this is that it basically eliminates data gravity. Often we will keep our data in one cloud like AWS and stream it to another cloud like Oracle or CoreWeave or Crusoe. And there's really no slowdown and no issue there. In fact, for our MPT models, I believe one of them, the data lived in AWS in California and was trained in Oracle in Australia. And we still experienced no slowdown. Now, for those of you who deal with a lot of cloud stuff, you might say, but what about the egress costs? You have to pay kind of the network costs of transferring your data out of the cloud. It can get expensive, but so are GPUs, and we've done the math, and basically keeping it in just a cloud bucket, an S3 bucket, an OCI bucket, a GCP bucket, what have you, and then paying the egress fees to transfer it to another cloud, if you even had your data in one cloud and your GPUs in another, is like 1% to 2% maximum of a training run. And for longer training runs, kind of llama style, it's way less than that. So the cost increase is very small compared to the convenience. And if it's all in one cloud, there are no egress fees, and you're in a very happy place. So I highly recommend this. It's a great tool. I'm not just shilling it because it's a MosaicML tool because we make no money if you use this. It's just open source. But personally, having used a lot of different tools over the years, I found it to be valuable, and the engineers who built this did a great job. So with that, we're kind of at the end. I want to end by reiterating my friendly advice, and then we can do some questions. Number one, start small and work your way up. Really, really start small. Don't spend your whole budget right away. Number two, be skeptical and be critical of what you read in the literature and what you see on Twitter and what your friend's friend at OpenAI told them and what have you. Test it for yourself. Not everything that you see in the literature is 100% reliable. And also, not everything is going to translate to your setting and your domain and what you're working on. Also, don't trust your intuition. A lot of counterintuitive things happen in deep learning. If you would have told me a few years ago that just making everything really big would have been enough to get us GPT-4 quality models, I would have laughed at you, and here we are. Test things for yourself. This really is science in its truest form and data science in its truest form, and you're going to have to be a scientist and follow the scientific method. With that, thank you. I'm gonna, grab questions with the 5 minutes we have left, and then we can wrap up. We have one question right away from YouTube. People would love to hear my take on the recent Phi 1.5 model and potential data contamination. I haven't read it in detail, and I don't want to comment on that. That's something to be adjudicated by the scientific community over time, and far be it from me to give answers on something I didn't build.
Thanks a lot, Jonathan. There is a question on determinism. How does determinism work? If you can talk in more details about it, isn't this quite tricky with distributed training? Not sure if this is about training or data loading, but...
I think this is about the streaming data loader and how it preserves determinism. The answer is it's really tricky, and the engineers have done a great job. They've especially had one really key idea, which is you have your physical GPUs, and then you can have the idea of virtual GPUs. And so as part of spinning up the streaming data loader, you actually set a number of virtual GPUs. And kind of the key idea is that your virtual GPUs have to be a number divisible by your physical GPUs or vice versa. But once you fix the number of virtual GPUs, you can actually change the number of physical GPUs as much as you want, and you'll preserve determinism. But it's the virtual GPUs that kind of determine the sequence that you look at the data. I thought that was a really neat idea. I wouldn't have thought of that, but it means that you can switch the number of GPUs you're training on and preserve full determinism. And if you look at some of our loss curves at Mosaic after resumption, it's identical. It'll go up and down exactly the same way. And that's due to determinism. Determinism makes debugging a lot easier. So it's nice that you can kind of get it for free without making any sacrifices.
Thank you. There are maybe the last question, because we're at almost at the end of the time that we have scheduled. There are several questions about fine-tuning data. Like how do you decide what to put into your fine-tuning data set? How do you evaluate the quality of it? Do you have any generic advice? It's obviously all use case specific, but any things that you have seen work or not work?
I think you can give the answer that I'm going to give, which is test it. Test it on small scale models and test it on small scale data sets and find out for yourself. That's the answer to pretty much every question here. Is there isn't really any generic advice. The advice is be a scientist. And spend your budget wisely. The rest is really, I wish we had hard and fast rules, but we're not there as a community yet. We're not there as a scientific field. And the best you can do is be a scientist yourself.
Maybe one final question, because I think you might have a good answer for this. What's your preferred framework for multi-GPU training?
So my preferred framework personally, I like our MosaicML LLM Foundry. So that's what we use for all of our models. It's built on PyTorch FSDP, fully sharded distributed or fully sharded data parallel. I always get those words mixed up, which I personally think is the best of breed distributed training library today. So that's kind of that's what we've preferred at MosaicML. Even if you don't use our code base, we really like PyTorch FSDP. Awesome. Thank you so much. This was a wonderful session. I really appreciate the questions. And I look forward to seeing everybody again in a couple of weeks.
Thanks a lot, Jonathan. We appreciate this session. This has been amazing. Thank you.